In this video, I'm going to be talking about cubic graphs as a bit of an introduction to this topic. I'm not expecting you to completely understand everything about cubic graphs yet. I just want you to have a vague idea of what we're talking about. So, an example of a really boring cubic graph is y equals x cubed. So this is the basic cubic graph. I know it's cubic because it's got an x cubed term. Just like a quadratic graph is one with an x squared term, a cubic graph is one with an x cubed term, which is a name that makes a lot of sense to us. So, here we have our table of values. So this is how we generally plot graphs when we don't know what they're going to look like. We draw a table of values out and we plot the coordinates. So negative 3 cubed is negative 27. Notice here we have to be careful because I'm doing a negative number times a negative number times a negative number. I'm doing negative 3 times negative 3 times negative 3. So we do actually get a negative answer. We get negative 27. Negative 2 cubed is negative 2 times negative 2 times negative 2. That's negative 8. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. Sorry, that should be an 8. And 3 cubed is 27. So if I plot those coordinates, then I get this sort of weird shape. Again, it's a weird curve. Doesn't look at all like the quadratic graph. And if I actually plot the lines in, then this is what we end up with. And you can see that we've got this weird business going on in the middle. We're sort of going up for a while, and then we curve in, and then we go back to going up. Okay? So that would be an example of a cubic graph. This is the graph of y equals x cubed. Now for this, we're not going to be looking at as many key features as we did for quadratic graphs, but we still know where the y-intercept is, in this case 0, and the x-intercept, in this case 0. Okay, here's another example of a cubic equation. It's one with an x cubed term. And through this, I'm going to teach you a little trick that we sometimes use when we're doing these kind of tables. I'm going to split up my rows a little bit more. Now this is only because it could be a little bit difficult to go, well, negative 3 cubed, take away 2 times negative 3. There's a lot of places to get lost there. So just as a bit of a tip, sometimes we split them up into 2 rows. There's absolutely nothing to stop you going straight from to completely cut out those middle 2 rows and just going negative 3 cubed minus 2 times negative 3 and put it in the y row. That'd be absolutely fine. This is just a little hint that sometimes makes the maths a little bit easier. So in this top row first, I'm going to do x cubed, which we just looked at. So negative 3 cubed is negative 27, negative 2 cubed is negative 8, negative 1 cubed is negative 1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. Now once I've done this, I'm also going to do separately negative 2x. Now notice that means negative 2 times x, which means we're going to again have to be extra careful because I need to do negative 2 times negative 3 to fill in that first box. So negative 2 times negative 3 is 6. Then negative 2 times negative 2 is 4. Negative 2 times negative 1 is 2. Negative 2 times 0 is 0. Negative 2 times 1 is negative 2. Negative 2 times 2 is negative 4. And negative 2 times 3 is negative 6. So if I put those two together, then that's how I get y, isn't it? If I have x cubed and I then take away 2x, then that's where my y comes from. So to find y in each of these columns, I just need to add these two numbers. So negative 27 plus 6 is negative 21. Negative 8 plus 4 is negative 4. Negative 1 plus 2 is 1. 0 plus 0 is 0. 1 plus negative 2 is negative 1. 8 plus negative 4 is 4. And 27 plus negative 6 is 21. Okay, so if we plot those coordinates, again, we've got this sort of coming up here, but then you've got this weird bit in the middle where it's really hard to tell what's going on. If I draw a line that connects all these dots, I can see that this is then the graph of y equals x cubed minus 2x plus, y equals x cubed minus 2x. So we've got this weird bit going on in the middle where it sort of dips and then goes back up. So this is another example of a cubic graph. Okay, now ignore the label because there isn't a +5. That's the next question. I've clearly not labeled this correctly. But again, we can label the key features of this graph. And this graph being y equals x cubed minus 2x. So the y-intercept here is where it crosses the y-axis. Again, just happens to be 0. But then, interestingly, we've got 1, 2, 3 x-intercepts. You've got 3 points where the line crosses the x-axis. Now, this isn't surprising. When we had quadratic graphs, we could have up to 2 places where it crosses the x-axis. We could have up to 2 x-intercepts. So with a cubic graph, where we've got the power of 3, we can now have up to 3 of these. And in this case, it's negative 1.41, 0, and 1.41. So if we get to a cubic graph, we can have up to 3 x-intercepts, which is fun. Okay, so this is actually going to be the graph of y equals x cubed minus 2x plus 5. If I do this as a table, then I can again use my tip from last time and fill in the 3 rows separately and then add them all together. And we did most of this already. Then the 5 row is really boring because it's just 5, 5, 5, 5, 5. But again, I can add these rows up because y is x cubed plus negative 2x plus 5. So if I add all 3 of these numbers, then I get y. So negative 27 plus 6 plus 5 is negative 16. Negative 8 plus 4 plus 5 is 1. Negative 1 plus 2 plus 5 is 6. 0 plus 0 plus 5 is 5. 1 plus negative 2 plus 5 is 4. 8 plus negative 4 plus 5 is 9. And 27 plus negative 6 plus 5 is 26. Okay, so if I plot these coordinates, and to make it very clear, I'm plotting the coordinate negative 3, negative 16. I'm plotting the coordinate negative 2, 1. Because that's the xy bit, that's the important part. I'm going to plot those coordinates. This is what I get. And if I look at this with the line drawn in, again, we've got a very similar shape. But this time, we have one y-intercept and again, only one x-intercept. In this case, approximately negative 2.09. We only have one x-intercept over here. So even though the shape looks very similar, it's still a slightly different graph because the x-intercepts are different. Okay, so the key points here. We can draw and recognize graphs of the form y equals ax cubed plus bx squared plus cx plus d, i.e. cubic graphs. Graphs with an x cubed term in. They can have 1, 2, or 3 x-intercepts. So we haven't yet seen any cubic graphs with 2 x-intercepts, but you might want to picture what one would look like. And you'll notice here that we can't have a cubic graph with no x-intercepts. And you also might want to think about why that is.